Engine overheating poses a significant threat to internal combustion engines, directly impacting performance stability and critically compromising long-term component longevity. Unchecked thermal excursions accelerate wear, warp metallic structures, and can lead to catastrophic engine failure. Understanding the intricate mechanics of the cooling system is paramount for mitigating these risks. The primary function of an automotive cooling system is to dissipate excess heat generated during combustion, maintaining the engine within its optimal operating temperature range, typically between 90 and 105 degrees Celsius. This complex network relies on a circulating fluid, known as coolant or antifreeze, to transfer thermal energy away from the engine block and cylinder heads. The radiator serves as the primary heat exchanger within this system. Hot coolant flows from the engine through its numerous fins and tubes, transferring heat to the ambient air facilitated by airflow. Common failures include external damage from debris, internal clogging from corrosion or debris accumulation, and structural fatigue leading to coolant leaks. A reduced heat exchange capacity directly elevates engine temperature. The water pump acts as the circulatory heart of the cooling system, mechanically driven by the engine's accessory belt. Its impeller forces coolant through the engine block, cylinder head passages, and into the radiator. A failing water pump often manifests as an audible grinding noise, visible coolant leaks from its weep hole, or a complete absence of coolant circulation, leading to rapid and severe overheating. Controlling the coolant flow is the thermostat, a temperature-sensitive valve located between the engine and the radiator. It remains closed during engine warm-up, allowing the engine to reach operating temperature quickly. Once the desired temperature is achieved, the thermostat opens, permitting coolant to flow to the radiator. A thermostat stuck closed prevents heat dissipation, while one stuck open delays engine warm-up and reduces heating efficiency. Coolant leaks represent a pervasive and often insidious threat to the cooling system's integrity. These leaks can originate from various points: deteriorated hoses, a compromised radiator core, a faulty water pump seal, or a corroded engine freeze plug. Even minor, unaddressed leaks gradually deplete coolant levels, reducing the system's capacity to transfer heat and inevitably leading to overheating. Radiator and heater hoses are critical conduits for coolant transport. Constructed from reinforced rubber, they are designed to withstand high temperatures and pressures. Over time, these hoses can harden, crack, or become brittle due to heat cycling and chemical exposure. Loose or damaged clamps further compromise the seal, resulting in pressure loss and external coolant leaks that diminish system efficiency. The radiator cap maintains the cooling system's internal pressure, which elevates the coolant's boiling point, allowing it to absorb more heat before vaporizing. A faulty radiator cap cannot hold adequate pressure, causing the coolant to boil at a lower temperature, leading to steam expulsion and significant coolant loss. This directly compromises the system's ability to cool the engine effectively. The cooling fan, whether mechanically or electrically driven, is essential for airflow through the radiator, especially at low vehicle speeds or while idling. A malfunctioning cooling fan, due to a broken motor, seized clutch, or electrical fault, prevents sufficient heat dissipation, causing engine temperatures to rise significantly, particularly in stop-and-go traffic. Head gasket failure is a severe consequence of prolonged or severe overheating. The head gasket seals the combustion chambers and prevents coolant and oil from mixing. When compromised, combustion gases can enter the cooling system, creating excessive pressure, or coolant can leak into the engine oil, leading to lubrication failure. Symptoms include white exhaust smoke, coolant loss without external leaks, or milky oil. Initial diagnostic steps for overheating often involve visual inspection. Check the coolant reservoir level and examine the radiator and hoses for any signs of external leaks or damage. Observe the temperature gauge for consistent readings. Fluctuations or immediate spikes often indicate a system anomaly. Ensure the radiator fan activates when the engine reaches operating temperature. A pressure tester is an invaluable tool for pinpointing external and internal coolant leaks. By pressurizing the cooling system to its specified operating pressure, technicians can observe a pressure drop on the gauge, indicating a leak. Visual inspection while the system is pressurized often reveals the exact source of the leak, whether it be a hose, radiator, or fitting. Thermostat function can be evaluated by monitoring the engine's warm-up cycle. If the upper radiator hose remains cold while the engine heats up, the thermostat may be stuck closed. Conversely, if the engine takes an unusually long time to reach operating temperature, the thermostat might be stuck open. An infrared thermometer can also measure temperature differentials across the radiator, providing insights into coolant flow. Preventative maintenance is crucial for cooling system longevity. Regularly flush and replace coolant according to manufacturer specifications to prevent corrosion and maintain heat transfer properties. Inspect all hoses for cracks, swelling, or softness and tighten any loose clamps. Ensure the serpentine belt is in good condition to drive the water pump effectively. Proactive management of your vehicle's cooling system directly translates to enhanced engine health and reduced unexpected breakdowns. Understanding these common failure points and implementing regular diagnostic and maintenance routines empowers vehicle owners to effectively mitigate the risks of engine overheating.